Mars glows in our night sky, a distant ember that has captivated humanity for millennia. Its red hue, vast canyons, towering volcanoes and polar ice caps tell a story of extremes and ancient mysteries. Once, water may have flowed here. Today, Mars stands as a frozen monument, silent, beautiful, and forever calling us to explore its secrets. For over a century, visionaries and scientists have imagined a transformed Mars, no longer barren but alive. This is the dream of terraforming, turning a lifeless world into a second Earth. Imagine green plains, flowing rivers, and breathable air under a blue sky. Terraforming Mars is humanity's boldest idea, an ultimate test of our creativity and ambition. The dream of a green Mars is moving from fiction to science, challenging us to imagine what's possible. Tonight on Skyward Space Quest, we ask, how close are we to turning Mars green? From bold engineering, factories, asteroid impacts, giant mirrors, to experiments like MOXIE and extremophiles, the quest to terraform Mars is both a scientific and ethical challenge. Are we ready to reshape a world? Terraforming Mars is a marathon, not a sprint, a project spanning generations. First, we must warm the planet and thicken its atmosphere, shielding it from deadly radiation. Only then can life take root, starting with hardy microbes and eventually, forests. This is a challenge of patience, vision, and perseverance. The question is, are we ready to begin? Earth is our vibrant, fragile cradle, our only home in the vast cosmos. But our planet faces mounting threats, from climate change to sudden catastrophes. To secure our future, we must look beyond Earth. Mars, though challenging, stands out as our most promising backup, a world that could one day become a second home for humanity. Mars stands out as our most familiar neighbor, a world with days and seasons much like our own. Its day is just over 24 hours, and its tilted axis brings seasons, echoing Earth's rhythms. Ancient river valleys and deltas reveal a wetter past. Today, vast water ice lies frozen at the poles and underground. The key ingredient for life, water, is already here, waiting to be unlocked. Mars is a world of stark contrasts, familiar yet profoundly hostile to life. Its thin carbon dioxide-rich atmosphere offers no protection from deadly radiation or extreme cold. Water cannot survive on the surface, and the weak gravity and lack of a magnetic field leave the planet exposed. Mars has good bones, but it lacks the protective skin and warm breath of a living world. For over 50 years, humanity has sent robotic vanguards to Mars, our scouts in a new world. These orbiters, landers, and rovers have mapped its surface, analyzed its geology, and tested vital technologies. The MOXIE experiment has even produced oxygen from the Martian air, a monumental proof of concept. If any world beyond Earth could one day be made habitable, Mars is the one. Our robotic pioneers have already taken the first steps. Establishing a self-sustaining human presence on Mars is the ultimate insurance policy, safeguarding humanity's future. By expanding to Mars, we create a second branch of civilization, resilient to catastrophe. The challenges will drive innovation and sustainability, benefiting Earth. Mars is not a perfect second Earth, but it is the best raw material we have, a world waiting for life to return. The case for Mars is a case for hope. To transform Mars, we must first warm the planet, raising its temperature above freezing so water can flow. This means creating a powerful greenhouse effect, thickening Mars's thin atmosphere to trap heat. As Mars warms, frozen carbon dioxide would turn to gas. amplifying the effect in a positive feedback loop. Scientists propose manufacturing greenhouse gases, importing them, or using orbital mirrors to jumpstart this transformation. Imagine Mars dotted with automated chemical factories, not making cars, but pumping out superpotent greenhouse gases called perfluorocarbons or PFCs. These synthetic compounds trap heat thousands of times more effectively than carbon dioxide. Robotic landers would deliver and assemble these factories, which mine Martian soil for fluorine and extract carbon from the air. The factories synthesize PFCs and vent them into the atmosphere, triggering a rapid temperature rise, potentially 5 to 10 degrees Celsius in just decades. This method uses local resources, avoiding the need to ship massive supplies from Earth. The process is gradual and controllable. If things go wrong, the factories can be shut down. Industrial chemistry and robotics, technologies we already know, could be the key to thickening Mars's sky. Building a network of PFC factories on Mars would be a colossal engineering challenge. We'd need hundreds of factories delivered by countless rocket launches, all operating autonomously in a harsh, unpredictable environment. These facilities must endure extreme cold, abrasive dust and global storms, relying on advanced robotics and likely nuclear power for energy. Mining fluorine is a major unknown. Its abundance and accessibility on Mars remain unproven. Geological surveys would be essential before construction could even begin. The scale, cost, and complexity of running a planetary industry for centuries is staggering. Turning this vision into reality would push our technology and cooperation to the limit. Another bold idea: redirecting ammonia-rich asteroids or comets to collide with Mars. These impacts would deliver greenhouse gases and nitrogen, thickening the atmosphere and raising temperatures. Spacecraft would nudge icy bodies from the outer solar system onto collision courses with Mars, aiming for a series of controlled impacts over decades. Each impact vaporizes ammonia and water, injecting heat and volatiles into the air. This brute force approach could double Mars's atmospheric mass with a single well-aimed asteroid. The result: higher pressure, more warmth, and a better chance for liquid water. It's cosmic engineering on a spectacular scale. Redirecting asteroids is risky. Precision is everything. A miscalculation could send a projectile toward Earth or create a planet-wide dust cloud, cooling Mars instead of warming it. Using many small impactors instead of a few large ones could reduce risks and allow for more controlled warming. But this multiplies mission complexity, requiring a fleet of spacecraft managing hundreds of objects. The political and ethical stakes are enormous. Asteroid-moving tech could be weaponized. Global cooperation and strict oversight would be essential. The power to move worlds demands extreme caution. A more elegant solution: giant orbital mirrors or soletas reflecting sunlight onto Mars. These mirrors would focus energy on the polar caps, sublimating CO2 and thickening the atmosphere without adding chemicals. Constructed in space from ultra-light materials, the mirrors could be adjusted or turned off as needed. This method is clean, reversible, and precise. No risk of runaway warming or catastrophic impacts. Mirrors could also support future settlements by providing extra light and warmth. It's a flexible tool for planetary engineering. Sometimes the simplest solution is just a little more sunlight. Even if we thicken Mars's atmosphere, it will slowly leak away, unless we solve a deeper problem. Mars lacks a global magnetic field, leaving its air vulnerable to the solar wind, which strips away the atmosphere over time. Earth's magnetic shield protects us. Mars lost its own billions of years ago. Any terraforming effort is doomed unless we can seal the bucket and stop atmospheric escape. Without a magnetic shield, all our work could be undone in millennia. The real challenge, creating an artificial magnetosphere to guard Mars's new air. Before we build a new world, we must first protect it. Imagine shielding Mars from solar wind, not by changing the planet, but by placing a giant magnetic shield in space at the Mars-Sun L1 point. This NASA concept would deflect charged particles, creating a protective shadow around Mars. The result? Mars could retain its atmosphere and block harmful radiation, key steps for future colonists and terraforming. While the L1 magnetic shield concept is scientifically sound and elegant in theory, its practical implementation would be a technological endeavor of truly Herculean proportions. The core of the shield would be a massive electromagnet, most likely a superconducting coil several kilometers in diameter. Superconductors are materials that can conduct electricity with zero resistance, allowing for the creation of incredibly powerful and stable magnetic fields without generating massive amounts of waste heat. However, to achieve their superconducting state, these materials must be kept at extremely low, cryogenic temperatures, just a few degrees above absolute zero. Building and operating such a device in the vacuum of space presents a formidable set of challenges. First, we would need to manufacture and assemble kilometers of superconducting wire, a task that would almost certainly need to be done in space using materials mined from asteroids or the moon to avoid the prohibitive cost of launching it all from Earth. Then, we would need a colossal refrigeration system to keep the entire coil at its required cryogenic temperature, all while it is being constantly bathed in sunlight. This would require a massive system of radiators, a cryocooler, to dissipate heat out into space, which is, honestly, a significant engineering challenge in its own right. The entire apparatus would also need a continuous and enormous supply of power, likely on the order of several gigawatts, to maintain the magnetic field and run the cooling systems. This is equivalent to the output of several large nuclear power plants on Earth. Such power would have to be generated in space, most likely by a dedicated massive solar power station, or a powerful, space-rated nuclear reactor deployed alongside the shield. The scale of this power requirement alone places the project at the very edge of our technological horizon, demanding significant advances in space-based power generation and management. Finally, the shield itself would need to be incredibly durable, designed to operate autonomously for centuries with minimal maintenance. It would be a solitary sentinel in the harsh environment of deep space, constantly exposed to the risks of micrometeoroid impacts, solar flares, and the very radiation it is designed to deflect. It would require advanced self-healing materials and sophisticated robotic systems to monitor its health and perform repairs. While technologies like in-space manufacturing, space-based solar power, and durable high-temperature superconductors are all progressing rapidly, integrating them into a single, reliable system of this magnitude remains a challenge for the distant future. An alternative, and perhaps even more ambitious approach to restoring Mars's magnetic protection involves working on the planet itself. Instead of building an external shield, some concepts explore the possibility of restarting Mars's own internal magnetic dynamo, or creating a network of powerful localized magnetic fields. This would be a more natural solution, mimicking the way Earth protects itself. However, it would require a far deeper understanding of planetary geology and the ability to undertake engineering projects on a subterranean planetary scale, a feat that is far beyond our current capabilities. One idea involves trying to re-liquefy portions of Mars's solid iron core. This could theoretically be achieved by drilling deep into the planet's mantle and detonating a series of powerful thermonuclear devices, or by focusing immense amounts of energy downward from the surface. The goal would be to generate enough heat to melt a section of the core and, by inducing a rotational flow, restart the convection currents needed for a planetary dynamo. This is a highly speculative and incredibly risky proposal. The energy required would be astronomical, and the potential for unintended geological consequences, such as triggering massive planetary-scale earthquakes or volcanic activity, would be immense and unpredictable. A more localized and perhaps more achievable approach would be to create a patchwork of smaller, artificial magnetic fields on the surface and in the lower atmosphere. Mars still retains pockets of crustal magnetism, remnant magnetic fields locked into ancient rocks from the time when its global dynamo was still active. We could potentially amplify these existing magnetic islands. One method proposes laying down vast networks of superconducting cables and loops across the surface, creating a series of powerful regional electromagnets. These magnetic safe zones could be centered over future population centers or key ecological restoration areas. Over centuries, as our industrial capacity on Mars grows, these individual magnetic islands could be expanded and linked together. By driving powerful electrical currents through naturally conductive layers in the Martian crust, or by embedding ferromagnetic materials like iron and nickel into the ground along specific pathways, we could gradually build up a more cohesive, planet-wide magnetic shield from the ground up. This approach would be incremental, allowing us to protect small areas first and expand the shield as our needs and capabilities grow. However, it would require detailed geological mapping of the entire planet, and major advances in situ resource utilization and large-scale power distribution on a planetary surface. Regardless of the method chosen, the distant L1 shield or the ground-up crustal network, the restoration of a magnetic field is not an optional extra in the terraforming toolkit. It is an absolute necessity for the long-term success of the project and the survival of any life on Mars, including our own. Without a magnetic shield, a newly created atmosphere would be a fleeting achievement, a temporary state of affairs destined to be eroded by the solar wind over thousands of years. It would be like trying to build a sandcastle just below the high tide line, a beautiful but ultimately doomed effort. The magnetosphere is the foundational element that makes all other aspects of terraforming sustainable. The protection from radiation is equally critical. The current Martian surface is bathed in a daily dose of radiation that is hundreds of times higher than on Earth. This level is sufficient to cause severe health problems for human colonists, including cancer and cellular damage, and would be lethal to most plants and animals exposed on the open surface. While early habitats could be built underground or heavily shielded, the ultimate goal of terraforming is to create a world where life can exist in the open, under a blue sky. This is simply not possible without a magnetic shield to fend off the constant rain of high-energy solar and cosmic particles. The presence of a magnetosphere would also have other, more subtle benefits. It would protect the delicate electronics of our robotic systems and surface infrastructure from being fried by solar flares. It would also help to contain the planet's water. The solar wind is not only effective at stripping away atmospheric gases, but it also breaks apart water molecules in the upper atmosphere. The light hydrogen atoms can then easily escape the planet's gravity, representing a permanent loss of this precious resource. A magnetic shield would protect the water vapor in the atmosphere, ensuring that the planet's water cycle remains a closed and stable system over geological timescales. Ultimately, sealing the air is the step that transforms our efforts from a temporary planetary engineering project into the creation of a truly stable and self-sustaining second home. It is the act that ensures our investment of time, resources, and energy will endure for millennia, providing a lasting haven for future generations. Once the atmosphere begins to thicken and temperatures rise, the next chapter of terraforming can begin. We transition from physics and chemistry to the magic of biology. Introducing life to Mars marks a profound turning point. Extremophilic microbes will be the pioneers of a new Martian ecosystem. These organisms are survival experts ideal for Mars. They will be dispersed by rovers or drones in selected regions. The goal is to establish resilient microbial oases. This process will be slow, measured in centuries. These microbes will enact profound changes on Mars. They will lay the groundwork for complex life to follow. Among extremophilic microbes, cyanobacteria stand out as Martian pioneers. Billions of years ago, they transformed Earth's atmosphere with oxygenic photosynthesis. On Mars, engineered strains could survive harsh conditions, produce oxygen, and lay the foundation for living soil. These remarkable organisms would be the first step in turning the red planet into a world capable of supporting life. Mars's regolith is not soil, it's lifeless dusty rock. To grow plants, we must transform it. Cyanobacteria and engineered microbes would create organic matter, fix nitrogen and break down minerals. Over time, this living carpet would hold moisture, stabilize dust, and prepare Mars for life. The first Martian topsoil, an unsung but heroic achievement. As Mars' atmosphere thickens and primitive soil forms, the first green shoots, lichens and mosses begin to appear, bridging the gap between microbial mats and true plants. Hardy and resilient, these pioneers break down rock, enrich the soil, and release oxygen. In biodomes, more complex plants and crops follow, accelerating oxygenation and food production. The first fern frond unfurling under a pink sky marks a milestone. Life is taking hold on Mars. The final, crowning achievement of biological terraforming would be the planting of the first trees. Trees are the master architects of terrestrial ecosystems. They act as powerful carbon sinks, create stable microclimates, drive the water cycle through transpiration, and produce enormous quantities of oxygen. The establishment of self-sustaining forests would mark the point where the Martian biosphere truly comes of age. However, the first trees planted on Mars would not be the familiar oaks or redwoods of Earth. They would need to be radically engineered organisms, designed from the genetic level up to survive and thrive in a world that is still a pale imitation of our own. These Mars trees would likely be based on hardy, fast-growing terrestrial species like poplars or willows, but their genetics would be heavily modified. We'd engineer them for extreme cold tolerance, allowing them to survive the frigid Martian nights. Their vascular systems would be designed to function under lower atmospheric pressure, and their leaves would be optimized for photosynthesis in the high carbon dioxide environment. They might even be engineered to have darker bark and leaves to absorb more sunlight and keep themselves warm. These trees would be planted first in the most clement regions of the planet, perhaps in deep sheltered valleys like Valles Marineris, where air pressure is highest and temperatures are most moderate. These initial forest oases would become the ecological powerhouses of the new Mars. They would act as giant humidifiers, pumping vast quantities of water vapor into the atmosphere through transpiration, which would increase humidity, form clouds, and promote precipitation. They would be massive oxygen factories, their collective photosynthetic output making a significant contribution to building a breathable atmosphere. Their extensive root systems would stabilize the newly formed soil, preventing erosion and creating a rich subterranean habitat for fungi and other decomposers, thus closing the nutrient loop. As these first forests took hold and flourished, they would begin to spread, their seeds carried by the wind to colonize new territories. Even with the most advanced genetic engineering, the greening of Mars would be a project of millennia. The vision of a planet covered in lush, continuous forests and grasslands is one that lies in the very distant future. It might take 500 years of sustained effort just to see the emergence of localized lakes and the first patches of green tundra and forest. Full planetary greening, with open-air ecosystems sprawling across continents, could easily take several thousand years or more. Yet each biological milestone, from the first surviving microbe to the first self-sustaining forest, would represent a monumental victory. It would be a step-by-step transformation, the slow, patient, and deliberate awakening of a sleeping red world. Before we send even a single microbe to Mars, we must confront profound ethical questions. Do we have the right to transform another planet, or should we preserve Mars in its untouched state? International laws and strict protocols exist to prevent contamination, protecting both Earth and Mars. Terraforming would require a global conversation and a fundamental shift in policy, one that cannot be taken lightly. What if Mars is not lifeless? Beneath its harsh surface, life may still exist, hidden in underground aquifers or briny pockets. If so, introducing Earth microbes could trigger a planetary extinction, erasing a unique genesis before we even discover it. How certain must we be that Mars is sterile before we risk everything? The answer reveals our values as much as Mars's secrets. Should Mars remain untouched, a monument to the universe's natural processes, or should we transform it, bringing life to a barren world? Some see terraforming as planetary imperialism, erasing Mars's unique history. Others argue it's a moral imperative, an act of creation expanding life's reach. The choice, preserve a silent desert, or create a second living world. Our decision will shape the future of life in the cosmos. Terraforming Mars would be a political challenge unlike any before, demanding global cooperation, new laws, and a shared vision for humanity's future. No single nation or corporation could decide alone. It would require a new international agreement. The decision to reshape Mars belongs to all of us, present and future, calling for unity, wisdom, and a grand conversation on Earth. The journey to terraform Mars has already begun. Technologies like MOXIE, which produces oxygen from the Martian atmosphere, are proving we can create life-sustaining resources on another planet. These early successes mean future colonists won't need to bring all their air from Earth. Autonomous robots are also learning to build and operate on Mars, laying the foundation for a sustainable future. Terraforming Mars demands moving massive equipment, factories, reactors, construction robots, from Earth. For decades, launch costs made this seem impossible. But with reusable heavy-lift rockets like Starship, sending huge payloads to orbit is now feasible. Yet many structures are too big to launch whole, they must be built in space. Advances in in-space assembly and robotics are turning this vision into reality. Terraforming Mars demands immense reliable energy, far beyond what we can ship from Earth. Next-generation nuclear reactors and advanced solar arrays promise to power this transformation. Compact, safe reactors and vast solar farms will provide the backbone for a new Martian civilization, turning the red planet into a world of possibility. Engineering Mars isn't just about machines, it's about life. We can't simply bring Earth organisms, we must design new life using tools like CRISPR to survive Mars' harsh conditions. By studying extremophiles and engineering microbes, plants, and even trees, we'll create a living toolkit for terraforming. Piece by piece, we're building the future of a green Mars. Terraforming Mars is the ultimate test of human ingenuity and responsibility. It challenges us to master new sciences, build autonomous industries, and create a new biosphere. If we succeed, Mars becomes a second cradle for life, a symbol of hope, unity, and our will to explore. This act would forever change our place in the cosmos, securing humanity's future among the stars. The quest to terraform Mars is filled with immense challenges and uncertainty. Even if we never see blue lakes or green fields, the journey itself expands our knowledge, pushes technology, and unites us in a common purpose. The dream of a second Earth inspires us to reach beyond the horizon. The future is waiting to be written, and the stars are calling.